So this is an example of what the effect of stereochemistry might be in E2 reactions. So we start with either cis or trans. The bromo compound bromocyclohexane with the substituted at the 4 position, which is a D-butyl substitute. And one of the effect of a multi-substituted that often pushes most of the conformers in a particular way. So in the case of these reactions, if we start with exclusively cis or exclusively trans, this one is 500 times faster. Exactly under the same condition, when we use the cis isomer, this is 500 times faster than the one with the trans isomer. And we realize what happens here when we examine the stereochemistry of these conformers. And so when we have a cis, it forces the bromine to be in actual position because you have a D-butyl group that wants to be, which is a bulkier group, so that forces the smaller group bromine in actual orientation. On the other hand, in case of the trans, they are diequatorial. And if you follow the reaction of how it's going, in the case of both of them, what they want is an anti-orientation of the hydrogen. Why? If you examine the structures, that will become clear on a 3-dimensional model. So let's assume that in one case you have the substituent, that bromine, is in the actual position. And because the reaction happens simultaneously, if you look at the bromine, there is a hydrogen, at least in 2 different positions. Both of them are exactly anti to that. In other words, when the base is pulling out this proton, this orbital can overlap, generate the double bond here, kicks out the bromine. So they are orientation, therefore, this hydrogen and this hydrogen, they're both essentially anti-coplanar. They are all the same plane as well as anti to it. And so that anti-coplanar arrangement, which is shown here, so the hydrogen of interest is this. Those 2 hydrogens, both of them are anti-coplanar to bromine. So they are, the important part is actually that they are on the same plane, which means the orbital overlap is perfectly positioned to carry out simultaneously the removal of the bromine and hydrogen and making this compound. In the other case, where you have, let's assume that this is the bromine now, which is an equatorial conformer. And the problem with this one is that none of the hydrogens, the hydrogens are all gauche. Okay, 2 in 1. This one, they are not on the same plane. As a result, the orbital overlaps are not perfect in this case when the removal of the bromine happens. The actual bonds that are on the same plane are this one as well as, so the problem is therefore you cannot remove it simultaneously with that overlap of the orbital. And as a result, this one moves much slower because much more rearrangement needs to be done with that. As a result, this is a slower reaction. And therefore, we can predict based on that, whenever you want to have a good elimination reaction, ideally the leaving group should, in a 6-member ring system, should be in the axial orientation. If they are in equatorial orientation, it doesn't work very well. So you can also predict that if you have, as in the problem that they have given you, let's say a bromine, and in the third position you have a methyl group. Again, if you do the E2 reaction with this compound, the third position has 2 methyl groups. Again, you can examine the same way, where this is trans and this is cis. So the bromine, in this case, because of the relationship that they are trans, in case of 1,3 relationship, which is opposite of 1,2 and 1,4, that would be 1 axial, 1 equatorial. So this is the trans, and the cis one will have and therefore, ideally, this reaction goes much faster than that. So this is the effect of the orientation of the different groups there, and similar examples are also in your text that you can go through. But some of them involve really van der Waals interaction. When we talk about also the product, we can see another thing that happens when you force a reaction to go through either E2 or E1 reaction. If you carry out this reaction, obviously this is a condition where E2 reactions are carried out, you are going to get typically 2 products, and the predominant product according to Said's rule would be the one double bond in the middle, major, and then you also get a minor product where the double bond is terminal. So this is roughly about 75% and 25%. And the rate expression in this case, of course, involves the bromide and the base, which is potassium tertiary butoxide. Now the same reaction can also be carried out at a much slower rate. Yes?
Shouldn't this be E1 reaction?
No, this is actually E2.
But
because you're using a strong base.
it's not. I thought it was dependent if bromine was connected to the three carbons.
E2 also, one isomer dominates. It's a radiospecific reaction in which it kind of follows the same rule as well. What you are doing is you are pulling out any of the, this is the alpha position, and there are three beta positions.
Okay.
Right? You pull out the hydrogen from the beta position, and normally in same rule still applies in E2 reaction, where the hydrogen is more frequently will be taken out from here rather than the terminal carbon. So we do get the same distribution also in E1, but the E1 process is much slower. What happens is that if you don't provide a good base, but you provide the solvent, you can use either butanol. Let's keep the same solvent. We will change the solvent, but no base. So then the reaction is forced to go through an E1 process where you generate a carbocation that then goes to the product. So the first step would be formation of the carbocation, and then that gets removed by one of the alcohol moieties, the bases, and it generates the same set of products in approximately the same distribution. So this process is E1. And so we can use the same substrate. The only fundamental difference is in one case we provided a strong base that has the ability to pull out the proton. The other case, the base is actually the solvent, which cannot take part simultaneously by removing hydrogen and kicking out the bromine. Therefore, it goes much slower rate. This one can be completed within a few minutes, and this one will go for hours in order to get the product. Nevertheless, the distribution of the products is similar. However, the other thing that is also evident here is that the rate is based only on the concentration of the bromine, the alkyl bromide. Furthermore, if we change the substrate, then what happens is that for E1 reaction, the tertiary works better than secondary. And E2, even though all the substrates can't actually get involved in that, but the hydrogen that is particularly from where the hydrogen is pulled out, if that is crowded, the reaction gets slower. So in that case, the stereochemistry of any of the beta carbon is particularly important to recognize. So therefore, this reaction therefore goes through a formation of initially a cation such as this, which can then react with an alcohol obviously the other product also forms in a similar way. And the alcohol therefore pulls out the other group. And that can happen only after formation of the carbon cation. So this is the intermediate that is formed. Now there is one section I'm going to not discuss, and you are not responsible for that. Skip section 5.17, which involves isotope effect. And since we don't deal much with isotope effect in this semester, not much point in going to that. The isotope effect is actually used for doing the kinetics of reactions. Typically, you replace a hydrogen with a deuterium, and if it goes through a process where that deuterium is taken out due to the red intermediate state, then there is a huge effect on the kinetics. If it doesn't, then it has very little effect on the kinetics. Anyway, we won't go through that. Skip that section. Any question up to this point? Okay, we'll move on to next chapter, which is chapter 6. Which is actually now, we'll look at the reverse reaction. We looked at elimination, now it's the addition reaction on carbon-carbon double bond. So the addition reaction, obviously, as we can expect, we start with sp2 hybridized carbons, and then they add, let's say, AB, and they are added to this carbon. And the carbons become sp3 hybridized. So this is the fundamental reactions that we are now going to look at. And so let's start with hydrogenation. Hydrogenation is a process where both A and B are hydrogens that are added to the carbon-carbon double bond. Now, adding hydrogens to carbon-carbon double bond is actually an exothermic reaction. Heat is released. So this is an exothermic process. Nevertheless, the reaction by itself is extremely slow. You can add hydrogen to an alkene and leave it with that for a long, long time, and only a small portion will change. However, about 100 years ago, one of the French scientists discovered that if you use finely divided metals, certain metals, then the reaction is very, very rapid and carried out at room temperature. So what he found is that if you have an alkene and you add hydrogen in the presence of platinum, nickel, palladium, or rhodium, this particular metals, and used finally, initially he used only metals, and found that actually if you grind the metal to small powder, that actually works better. And we'll see why that happens. In fact, the alkene then gets reduced to alkane, and heat is released. So So negative delta H is positive or delta H is negative. So it means the same thing. It's essentially an exothermic reaction, heat is released. And for each double bond, essentially, it's about 150 kilojoules that are released in this process. So minus delta H is typically 136 kilojoules for each double bond. Now, one of the consequence that was initially noted is that the hydrogen is added from the same side. And in other words, the addition can take place either syn or anti. And the way we can actually look at it is, let's say you have a double bond. And now it can be added from the two different sides. So let's assume that then what will happen is that you get hydrogen, X, Y, and in the Solver's formula, then the other hydrogen will be added this way, A and B. So this would be anti-addition. Or it can happen on the syn addition, where both the hydrogen would come, let's say, from the top. So the other possibility would be that H, X and Y, and then H, A and B. So this is syn addition. And it turns out that when the stereochemistry were examined carefully, that always the hydrogen comes from the same place. So this is 100%, and this does not happen, particularly the hydrogen addition. And we understand when we follow the mechanism of this process. So the way this mechanism goes is as follows. Let's say the metal really helps to, so let's assume that you have a metal surface here. In the metal surface, you can have the hydrogen added to that, and when you add the hydrogens, they can be dissociated and hydrogens are sticking out on different surfaces, many of them. And the hydrogen bond is actually broken between the hydrogen. They also form a complex with the alkene, in which what they would do is replace the pi bond with two sigma bonds in step by step. So initially, it would form, say, the hydrogens are there, many hydrogens, and this is changed and anchored with the, so the pi bond is replaced with two sigma bonds with the metal. But these are very weak sigma bonds. And following which, the hydrogen can be added to one of the places. Then the fourth state also. So now this can be released from the metal surface. And again, by grinding the metal to dust, what happens is you increase the surface area of the metal. If you just have a plate of metal, compared to that, if you just really make it small, pieces that would just increase the surface area, and therefore there are more places to attack the hydrogen, and there are more places to attack the alkene, and therefore the reaction actually goes much better than just a sheet metal. Therefore, this is the reason that scene addition happens. They are both added from the same place. Yes?
After the first addition of the hydrogen, it's impossible for there to be a rotation around the single bond that could let you have the...
No, it's still anchored. It is possible, but it doesn't give it enough time to do it. So it's a fairly rapid process, so that's what they are adding. Okay, so in fact, we also see that in cyclic molecules where we can examine that addition. In many cases, after addition, they rotate, and therefore there will be mixed, as he mentioned, that, but this is more clear when you use a cyclic molecule such as this. So if you have now you tell me, if you know that addition is same, which one would be formed of the two products? First one or the second? The addition is same.
First
Both
one.
are coming from the same place. Diequatorial is trans. Right? So this is trans. The hydrogens are also trans, right? So that cannot happen. 100% of this product is generated for hydrogenation with any metal. No matter which metal you use, you still get the same product. This is the only product that's generated during the hydrogenation of carbon-carbon double bond in a cycle. Likewise, also there are more complicated molecules that we see where we can look at alpha pinene, a compound with bleach surface. So, So in this case, again, the effect that happens is that the double bond, both hydrogens come from the same side. But the important thing to also recognize that there may be a van der Waals interaction. In this case, if we in this particular case, really it's a van der Waals interaction of which side the hydrogen may come from. And if we look at the other hydrogen, in this case the hydrogen comes from the bottom. Why did I draw that? And in this case, the hydrogen would come from the top. And it turns out that again here, this is the 100% of the product. And this is not generated at all, because in this case, the hydrogen has to come from the top, and the top is blocked by the methyl groups. So the methyl groups really blocking the top face, and the hydrogen cannot come from the top, they must come from the bottom. As a result, the metal is turned equatorial because the hydrogen approaches from this side. Okay. And therefore, the hydrogen comes here and the metal group is pushed towards the equatorial side. The other approach from the top is blocked by the metal groups, the stereo. So one thing we see in this type of product is that the reactions could be stereospecific or stereoselective. The term stereoselective means more than one stereoisomers are possible to form, and one is formed in a larger excess. So one stereoisomer is formed in larger excess related to other stereoisomer or isomers. It could be more than two for that matter in some cases. But most often we deal with one or the other. And of course, whenever it's 100%, you can also call the reaction stereospecific. So we'll see examples of many of these reactions. The stereoselective reactions are very common. One stereoisomer is formed over another one because of either van der Waals interaction or the type of reaction that is taking place. And we'll discuss that as we go along with other reactions. So in terms of the heats of hydrogenation, again, the heats of hydrogenation are often used just like we have used combustion energy to look at the potential energy of various isomers. So the heats of hydrogenation So with stereoisomers, if we see that we have so these are all isomers. This is a constitutional isomer, and these two are stereoisomers. This is cis and trans 2-butene, and this is 1-butene. So, as we have seen in case of combustion analysis, that the potential energy of this is higher than the cis, and trans is actually more stable than cis. And so the difference between these two is 7 kilojoules, and between these two is about 4 kilojoules difference. And that is expressed also in their hydrogenation energy. The hydrogenation energy of delta H is 126. This one is 119, and this one is 150 kilojoules per mole. So they reflect their stability, and therefore we can compare stability using the various heats of hydrogenation of different molecules. And there is actually a table that gives you some of these numbers, and you'll see they all make sense in terms of which one would be more stable than another one. All right, so next move on to some other reactions, and this reaction is particularly important because, like the elimination, that also tells you the different types of reactions that have been formed. Okay, so this is unlike the hydrogen, which essentially adds 2 units of hydrogen. And so there is no relationship as to if you switch them, that will still give you the same product. But electrophilic addition of hydrogen halide, essentially you have to determine where the halogen will go and where the hydrogen will go. So to give you an example of this reaction, let's say if you have one butene, and then you add hydrogen bromide, for example, in the presence of a solvent such as acetic acid. So now, see, you can end up with 2 different bromides. In one case, the bromine can add at the very end. And the hydrogen can add here. And of course, you can also do this. So both products are possible depending on where the hydrogen goes and where the bromine will go. And it turns out that one of the colleagues of Zaitsev, his name was Markovnikov. He predicted which product would be formed in excess. Because again, this is a radio selective reaction. And this reaction, it turns out that according to Markovnikov, the hydrogen will be added to the carbon with a larger number of hydrogen. So in other words, when we compare any double bond, we see how many hydrogens are already there. And then based on that, we add the hydrogen to the one where more hydrogens are there. And therefore the bromine or the halogen would go to the other one. Okay, in this case, we have 2 hydrogens here and 1 hydrogen here. So the hydrogen must go to this one. And so this is the major product, according to Markovnikov. And the other one will be a minor product in the process. And we'll see in a minute why that is so. Because if you also follow the mechanism of this reaction, you will be able to see that why this particular reference of where the hydrogen will be added. So the explanation of the Markovnikov's rule is as follows. Okay, we start with what happens when a hydrogen halide is added. Now, let's add the hydrogen first. That is actually the way this reaction progresses. If you add the hydrogen, it's H plus that is added to one of them. And so possibility is that, let's say, we add to the first carbon, CH2, CH2, positive charge migrates here. The new hydrogen is added here. And as a result, the positive charge migrates on the other carbon. And if we do the reverse of that, then the hydrogen would be added here. So, and the positive charge would migrate there. Now tell me which one is a more stable carbon cation. This one or this one? The second one is a more stable cation. Therefore, there is a preference of forming this cation, which can then undergo the attack by Br minus and forming the product that we already have seen is formed in excess. So that's the mechanism. This is the predominant pathway. Yes.
In the first case, where you have the positive charge residing in the terminal carbon,
Yeah.
do you have a hydride shift from the second carbon?
Well, if it is a stable enough carbon cation, but in this case, we're just adding a proton, and therefore, initially, it's forming. This is extremely high energy to begin with, compared to that. So, if we actually follow the reaction process, the addition of hydrogen in one case is going to the secondary, and the other case that goes to the primary is much, much higher energy. Therefore, that's what determines the rate of reaction. Okay. And we'll discuss a little more of this in the next class. I'm not returning your exam today. It will be returned on Wednesday. I want to go through that again because there's a whole variety of numbers going anywhere from 30s to 90s. I just want to go over them again.